In Chapter 2, we're going to be going through electrostatic forces and fields. Now, this is really an introduction to electricity in general. And because it's an introduction, it is going to be fairly long. That's why it's going to last a couple of weeks. So not only are we going to talk about electric forces and electric fields, we're going to move on to electric flux and our first Maxwell's equation, Gauss's law. So there are a lot of topics within this chapter that you do have to become familiar with, which is why we want to spend extra time going through the concepts and going through practice problems. So what are we going to talk about in this chapter? The first thing before we even start the chapter is to go through a recap of calculus and vectors and some units and constants that you should have learned in your Math 127 and 128 courses, as well as your first and second physics courses. Now, after we go through a review of calculus and vectors, we want to tackle the main concepts and problems within electric forces and fields. So the things we are going to go through are electrostatic charge, basically what makes up a charge, go from that charge and talk about the forces between two charges, whether positive or negative, and electric fields that are generated from those charges. Once we have a thorough understanding of electric charges and fields, then we can talk about electric flux, which has to do with how many electric field lines penetrate a specific surface. And by having a full understanding of all of these, we can move on to deriving Gauss's law and applying it to determine the electric field in different scenarios. So let's first go through a math review. We're going to go through calculus and vectors very briefly, and most importantly for this course, we do want to have a thorough understanding of coordinate systems. So the first quiz that's going to come up this week, or technically quiz number 2, will tackle coordinate systems, as well as a general conceptual understanding of electric forces and fields. So let's first start off with the basics. What are functions, variables, and constants? A function is a rule that associates a y value for every x value. So how does a function work? You have an input x, it exists in a domain, it's a variable that we choose, it's an independent variable. And when we put it through a function, we're going to get an output. And that output called y is called a dependent variable. It depends on the choice we make for x. And for input and output, inputs exist in what we call a domain, and an output exists in what we call a range. So this is stuff that should, be very familiar to you if you've taken the 2 calculus courses already. And as we move on to different topics in E&M, we should really understand the fundamental graphs of functions. So definitely know what x squared looks like, a sine function looks like, so on and so forth. Because for a lot of the different problems that we encounter, we're going to need to know how to draw a plane, or either 2D or 3D plane. We're going to have to know how to label the axes. And we also have to be able to draw and label curves and mark different points on those curves that are important to us. So in order to do all that, it means we have to be familiar with understanding the different coordinate systems. So when we talk about any coordinate system, we have to first take a look at the different points to consider. For any coordinate system, I've just kind of drawn a bluish curve here, or a blob. We always have an origin to our coordinate system, which we have as O in red over here. We then have an arbitrary point on the curve or the object, which is our choice. So we use A, and we have a point P in green, which is a point in space where we make our observations. So these are the 3 points that are typically used in any coordinate system within the questions that we'll encounter. And depending on what kind of question you have, you can define r as the distance between 2 points. So in this case, I have r as the distance between A and P. I have r1 between O and A, and r2 between O and P. It doesn't have to be r, r1, and r2. You are more than welcome to choose r to represent whichever points are more convenient. Typically, we use r to represent the distance from the origin to some sort of arbitrary point on the object. So before I go into coordinate systems, I do want to do a brief review of vectors and scalars, because once we move into 3D coordinate systems, you do need an understanding of vectors. So when we discuss physical forces and fields, we also have to understand how to deal with vectors and scalars. A vector, you should all know in physics that it's a value that has a magnitude and a direction. Now, if you're talking about a scalar, it's just a number that has a magnitude and no direction. So with vectors and scalars, we also know that there's dot products and cross products. Dot products are those with scalars as a final value, and cross products will end up with a vector. So in order to do these calculations, there is also another component that we should know of, and it's called the unit vector. And why we introduce the unit vector is because it will be very important as we move on in E&M to figure out what direction specific components are in. So let's first define the unit vector, and then we'll give it some purpose as we move on throughout the lecture. So if we have a vector A with this arrow on top to represent its vectorial component, its magnitude is represented by the absolute value bars of A, and its direction is an A hat. So keep in mind the different notation for each of these. If we're just talking about the vector itself with a magnitude and a direction, we have A with the arrow. For a magnitude, we have the 2 bars, and then a direction, we have the A hat. Now, for the direction A hat, we call it the unit vector, which has a magnitude of 1, and it's in the same direction as the original vector, and it's defined as follows. You have A hat being equal to the total vector component divided by the magnitude of the vector. And that basically means that you have a value of 1. Also note that there is a position vector r hat, and that defines the distance between 2 points on a coordinate system. And this is something we'll talk about once we move on to electric forces and fields. Now, moving on, now that we know that what vectors are, basically magnitude and direction, we move on to the dot product. We can do different types of multiplications when we have vectors. So let's first define 2 vectors, A and B. I have A in blue going up this way, and I have B being pretty flat over here in green. And when we take a look at these 2 vectors, always note that these 2 vectors, if we're doing some sort of operation with them, they have to be related to each other in some way. And the only way we can relate the 2 of them together is by an angle. So we kind of piece these together and say that there is an angle theta between the 2 vectors. And that angle is really important when it comes to the dot product and the cross product. So the dot product requires us to multiply the component of one vector in the direction of the other. So that essentially gives us 2 options. We can have A dotted with B or B dotted with A. So what does this mean? It requires us to multiply the component of one vector in the direction of another. And we have these 2 options. I'm going to take a look at option 1, where we take a look at the component of A that's in the direction of B. That means in A, I project my vector down towards this flat green surface, and I have the x component of A to represent the fact that it's on the x-axis, assuming this is the x-axis. So I'm going to multiply AX by B to get my final answer, because that's the projection of A onto B. Now I can also look at it the other way. Maybe I want the component of b that's in the direction of a, so I have bx going this way. So then I can do another calculation as well. So let's start over here. How do we get to ax? In order to get to ax, we do need to know this angle theta over here. So we have using trig functions, we know that the cosine of theta is equal to adjacent over hypotenuse. So that means ax is equal to a cos theta. So that means to multiply these two together, ax times b, we have a cos theta times b, and we get ab cos theta. Now we try the other way. How do I get the component of b along the vector a? So I now take a look at this triangle. I need to figure out bx, which is this way. I also know that cosine of theta is equal to adjacent, which is bx over b. So that means I know that bx is equal to b cos theta. So I know it's going to be b cos theta times a. So in this case, I have b cos theta times a. It's also equal to ab cos theta. So as you can see, it doesn't matter if we do a dotted with b or b dotted with a, you get the same answer. It is a scalar answer, and because you can flip them around and get the same answer, they are called commutative. So moving on, we have the cross product. The cross product is very useful when we want a third vector that's orthogonal or 90 degrees to both vectors a and b. And this is very useful when it comes to coordinate systems, because the Cartesian coordinate system with x, y, and z, you can pretty much point your fingers using the left-hand thumb rule in the direction of vector 1, 2, and 3. So if I do this with my fingers, this is my left hand. I have the video reversed. So let's actually try. No, this way is better. So if you're looking at your own finger, you can have vector 1 going this way, vector 2, and vector 3. So I'm usually going to cross vector 1 with vector 2, and vector 3 will be in the direction that's orthogonal to both of these. And this is something that we'll discuss quite a bit once we get into electric fields and also magnetism. Okay, so now we have a pretty thorough understanding of just basic points to consider for a coordinate system, as well as vectors and scalars. Now we can actually do a discussion about derivatives and integrals and calculus, and how that applies to different coordinate systems. So I'm going to first start off with derivatives versus integrals. A derivative, if you take a look at this, we have a curve over here in blue called f of x, and we've marked out 2 points here from a to b. Now for a derivative, usually we want to figure out the slope of a curve at a specific point in time. So if I want to figure out the slope of the curve at x equals a, then I find the point of f of x equals a, and I derive the slope at that point. So the way we mark that is d over dx of f of x. And that is us taking the derivative. Now, the integral determines the area underneath the curve between 2 points. So I have the integral from a to b of this function with respect to x. So that means I'm trying to figure out the area underneath in green. So unfortunately, this is where it gets tricky. The dx over here represents a differential element, and in E&M, we're going to have to be familiar with switching between different coordinate systems. So it's these differential elements that will change all the time, depending on what scenario we're looking at. Sometimes we have a linear situation, in which case we're looking at dl, a change in length. Sometimes we have a differential area element. We have a surface that we're looking at, and we have to look at ds, which now gives us a double integral because it's a length times width component. And then sometimes we have a volumetric differential element. So we have length, width, and height. So we'll have potentially dx, dy, dz, and end up with a triple integral. So what I'm saying is for this course, the most important thing is to figure out what coordinate system you're using and to be able to set up the equations properly, because the math itself won't be as important as the setup. So in this course, being familiar with integrals is extremely important. And don't worry about it for now, because we will have tons of practice to get you up to speed. So when we're talking about coordinate systems, the one that you're most familiar with is the Cartesian coordinate system. So it has 3 unit vectors, x, y, and z. So you have x, y, z going this way. A vector A in 3D space can be represented by the path taken in each direction. So assuming you have AX, AY, and AZ as the distances moved in the XYZ direction respectively, we then end up with a component form of the vector. We can have AX for the distance moved in the X direction, then AY in the Y direction, and then AZ in the Z direction to get to a specific point from the origin to that point to create that vector. Now, another important thing to note is that every time you have a coordinate system, if you have 2 or more, you're going to create different planes for us to work in. And once you have different planes, you will get different differential elements. So over here, I have the XY plane, or XZ plane over here, in which case Y is equal to 0. When X is equal to 0, you have the YZ plane, and when Z is equal to 0, you have the XY plane. And that plane in blue is the one that we're always most familiar with 2D graphs and calculations. Now, remember, our focus for E and M is to find differential elements to integrate with. So when we integrate, always just think of area to make things easier for yourself. With the Cartesian coordinate system, which we will symbolize using x, y, z, we have 2 options. We have we have 3 options. You can either have a linear option, in which case it's just one of these and you just have one line. But for our purpose, we just want to look at the 2D and 3D world, because that's where most of our calculations will be. Now, thinking of area, when we're talking about differential elements, remember what I said about integration. We have dx, but once we introduce an additional component, we have to consider looking at what our differential elements are for that component. So if I'm taking a look at a differential surface element, I have a differential surface or a differential area. You can use either of these two. They're the same. Whenever I'm looking at a 2D area, I know that I'm looking at a length times a width. My width, it's dx, so I have a differential change in the width, and I have a differential change in the length, dy. So I multiply these two to get a differential surface element. Now in the 3D world, I just simply add a third differential component, which is dz. So a differential volume element is dx times dy by dz. And that is created by a little cube from each of these differential elements. So think about it as you're trying to figure out the smallest component to an area, which is this, and the smallest component to a volume in each direction of your coordinate system. So hopefully that makes sense. We're now going to move on to polar coordinates, because the other 2 coordinate systems in 3D space, which are cylindrical and spherical, will require knowledge of polar coordinates. So why learn about polar coordinates is because sometimes when we have circular or arch components to a function, that's more easily if we have circular or arch components, sometimes it's a lot easier to describe them using trig functions. And when we use trig functions, Cartesian isn't the greatest coordinate system for that. So if you're trying to define a circle or something, it may be easier to go by radius, so r, a radial length, and also an angle. So here we have r, and then here we have phi to represent the angle or the azimuthal angle around the plane. And here we have all of the different trig identities to allow us to convert between the Cartesian coordinate system and the polar coordinate system. So just keep these in mind as you're working through the questions, because you can switch through them fairly easily, and we will go through some practice for that as well. Now, the only question is, when we switch to polar coordinates, how do we find the area? So we now have to not really look at straight lines, we have to look at curved lines, and that's where an arc length comes in. So it's the same idea. If I'm trying to take a look at the smallest area in this system, then it really is, I can take a slice of the pie and then a little wedge from that pie, and I want to find that small differential area. So in black over here, this is ds. I know that if I'm trying to find an area, it's still going to be length times width. I still need two components to create my area. The side length here is a change in radius, so I call that dr. But the curved length here is no longer straight. So that means I have to figure out an arc length. And the arc length is defined as r, the distance away from here, times the change in angle. So r times d phi will give us the arc length. So that should be something that you're familiar with already from angular momentum studies in physics 1 and 2. So when we're defining a differential surface element or surface area element, we have ds or dA being equal to r d phi dr, and that's in polar coordinates. So keep in mind, these are things that you don't have to derive every single time you start a question. You just have to pick the right one. So now that we know Cartesian coordinates and we know polar coordinates, we can move on to cylindrical coordinates, which is a combination of both. So think of this as a polar coordinate in 3D space. The only thing we're adding is that z component from the Cartesian coordinate system. So I have a diagram here where essentially we start off at an angle of 0, and in red we spin this blue line, an angle of phi, across to a specific area. We extend the line to a specific radius of r, and then we raise it up to a specific height to a point P. And so this is a cylindrical coordinate system because we have symmetry about the z-axis in this case. So always use the cylindrical coordinate system if you think there is symmetry around one axis. And if that's the case, then you can use polar for the planar surface, and then you can use the z-axis to raise it up a certain height. So when we're talking about cylindrical coordinates, we are for sure looking at things in 3D space. So that means we're looking at a differential volume element. So in the future, when we're trying to integrate, we want to take a look at the smallest volume that can be created from this. So how can I create the smallest volume? You can kind of see over here, the flat surface is that curved surface from the polar coordinates. And now we have some sort of height. And we also have a lot of sides to this because it's now 3D. So for a differential volume element, if you take a look here, I still have my dr in blue. I still have my arc length, r d phi in red. But now I have a height element, so I have to introduce a dz. So the differential volume element for cylindrical coordinates is simply dr times r d phi times dz. And we can just combine that to r dr d phi dz. So if you're ever integrating across a differential volume element and you've picked the cylindrical coordinate system, just use this. You don't have to derive it from scratch. Now, because we have this volume over here, sometimes you may just want to look at one of the surfaces, especially if you're taking a look at electric flux. Electric flux is how many electric field lines penetrate a particular surface. So if that's the case, then maybe you just want to take a look at the blue surface over here, which we call C. In this case, C is the area created by dz, the height, and r d phi. So we can just define the differential surface area element of C as dc. Similarly, we can do dB, which is dr times dz, and we can do dA, which is dr times the arc length r d phi. So these are just examples of how you can easily manipulate an equation based on the coordinate system that you choose. The last one that we want to go through is spherical coordinates. Now, what is an entirely new way to define a point without Cartesian coordinates? This is where we move on to spherical coordinates. We don't want to depend on how far something travels along the x, y, or z axis. We want to base everything on angles. So we are only looking at the radius, the radial length, and two angles. Number one, how far it spins away from the x-axis, and how far it spins away from the orthogonal axis of the plane. So this green angle here, theta, is called the polar angle. Sometimes it's called the zenith angle or the inclination angle because it gives it the height component. But the azimuthal angle is the one that we've looked at the entire time. It's the one that swings along the xy plane. Now, understanding what these two angles are is the first step. Next, we now have to take a look at how to create that 3D volumetric differential element. So, differential elements in spherical coordinates, we can find volume or area once again, but I just want to focus on volume over here. For volume, you have dr in purple, and over here, you now have r d theta because it's a change in the polar angle or the inclination angle, and that's an arc length. So don't forget, there's only one straight line in this 3D shape, and that's dr. The change in green and the change in red, they're both curved lines. So here I have r d theta, but now the curved red line is no longer r d phi. It's going to be defined as something else because there is some height to this. So we have to take a look. I know I have dr, and I know I have rd theta. Now I take a look at the azimuthal angle at the bottom, and I mark it out in blue. I know that this length in blue over here is going to be r sine theta. So keep in mind that's going to come from the angle that's created. So I'm going to go back to the previous slide right here. I know this is r. I know this purple line over here gives us r sine theta. And this purple line is exactly the same as this blue line. So that's why we can call this r sine theta. So using r sine theta as the length over here in blue, I now have this curved arc length as r sine theta d phi. So just keep that in mind. There is a completely different definition for the arc lengths when it comes to spherical coordinates. Once again, do you have to memorize this? No, because it's just given to you right here. So the three different elements that create that volumetric differential element will be dr in purple, r sine theta d phi from the red component, and r d theta from the green component. Combined, you have r squared sine theta dr d phi d theta. So you can just use that for the calculations. Now be careful with the volume bounds, especially for spherical coordinates if you're looking at a full sphere. The reason for that is because when you're integrating, you will have to figure out bounds for each of these elements, and this is something that we'll practice a lot of. In terms, if we're looking at a full solid sphere, we know that we have the radius going from 0 to the full radius capital R. So that's fine. Now, when we're taking a look at the azimuthal angle, we know that we're going to spin phi around from 0 to 360 degrees. And that's going to create a full circle. So that's going to go from 0 to 2 pi. Now, what about this polar angle, the inclination angle, theta? If I have a full circle and I spin it around 180 degrees, then I've already created a full solid sphere. So if I spin it around a full 360 degrees, I've created a sphere within a sphere. So that's too much integration. So just keep that in mind. If for your polar angle, you're only going to integrate from 0 to pi. So we'll do lots more practice with this as well and draw diagrams so that you can see and look at what you're trying to solve. In terms of derived units, this is just a list that I put together that will be handy as you move on through this course. You can print this off, do questions with it, but we will be looking at newtons for forces, joules for potential, amperes, volt, farads, and so on and so forth, mainly later on in this course. For physical constants, these are the ones that you should know of. You don't have to memorize them. And I won't be going through them one by one. But when it comes time to a test or an assessment, a formula sheet will be provided for the midterm and final assessments. And because it's open book policy, you can just download them and keep them handy with you.